Alright, we're moving on now to operations with a complex number when it's in polar form. Okay, so we've looked so far when it's been in what we call rectangular form. So if it's in the form a plus bi, for instance. Okay, but now we're looking at it in polar form, so r cis theta, or re to the I theta. Now, what we first of all need to understand is that addition and subtraction must be in rectangular form. Okay, so when we think about adding or subtracting complex numbers, we're looking at, say, 2 plus 3i minus 6 minus 4i. Okay, so we know that adding or subtracting complex numbers is we need to add and subtract the real and imaginary parts, and so we're going to get negative 4 plus 7i in this particular instance. Okay, so that's the form that it needs to be in if we're to add or subtract a complex number. But multiplication, okay, it's actually quite useful for it to be in polar form, and we'll show you why that's the case. So if we first of all have a look at two complex numbers, so z1 and z2. Z1 is given by r1 times cos theta 1 plus I r1 sin theta 1. Okay, or more simply, we might think of it as z1 equals r1 cis theta 1. Okay, and z2 equals r2 cis theta 2. Okay, so that's just that form. Alright, so that's polar form for both of those complex numbers. Now it can be shown, okay, we don't need to go through the process of proving it, but that if we multiply those two complex numbers together, then what we find is that we get r1 times r2, and that's multiplied by cos of theta 1 plus theta 2 plus I sin theta 1 plus theta 2. So in other words, when we multiply two complex numbers together in polar form, we multiply the moduli together and add the arguments. In other words, z1 times z2 will be r1 times r2 cis of theta 1 plus theta 2. So we're multiplying the moduli and adding the arguments. Okay, it really makes that quite easy to do then. So let's have a look at these two complex numbers that is given in polar form. So we've got 4 root 3 cis of negative pi on 3 for z, and 2 cis pi on 3 for w, and we're going to find z squared times w. Okay, so let's work through it. The first step is we want to find what z squared is. Okay, so there's our complex number for z, and it's being squared, and we multiply that by our complex number w. So first of all, squaring this, okay, because it's times itself, okay, then we multiply the moduli together. So in other words, 4 root 3 times 4 root 3, or 4 root 3 squared, and cis of our arguments which are added together, so negative pi on 3 plus negative pi on 3. Okay, so in other words, in this case we're doubling it, aren't we? Alright, so adding them together, we end up with negative 2 pi on 3. So that's the result of z squared, and so that then is what we're going to multiply by our complex number w, to cis pi on 3. So in doing that, we multiply the moduli, so 4 root 3 squared times 2. Now 4 root 3 squared, okay, is going to be 48, because 4 root 3 would be the same as 16 times 3 inside our square root sign, and 16 times 3 is 48. So square root of 48 times itself is going to be 48. We multiplied that by this modulus 2, and that's what we've got here. Okay, and that comes to 96. And the arguments we add together, so negative 2 pi on 3 plus pi on 3, and that's what we'll show here, okay, is going to be negative pi on 3. So that is our solution when, for this particular product. Okay, so that's for multiplying. Division, okay, what we do is a similar thing, okay. When we're dividing Z1 by Z2, we divide our moduli and subtract the arguments, okay. So it's just a very similar idea, okay. Divide and subtract rather than multiply and add. And now we look on at the complex conjugate in polar form. Now you remember that if we had our complex number Z as A plus BI, so in rectangular form, then the conjugate of that is A minus BI. Okay? In polar form, okay, our complex number Z is R cis theta. The conjugate of that is R cis of negative theta. If we were to write it in fully expanded form, then the conjugate is going to be R times cos negative theta plus I sine negative theta. Now let's think about the symmetry properties of the unit circle for a minute, okay, so that we've just got a full understanding of what we're looking at. Now if I'm just draw here our unit circle, and if we think about our angle theta, alright, so if we've got, that wasn't meant to happen, an angle there which is theta in our first quadrant, negative theta would go this way. Now cos, you remember, is our x-coordinate, okay, so what we find is if we were to draw our dotted line down here, cos of theta is the same as cos of negative theta. However, sine of theta is not the same as sine of negative theta. They're the same absolute value, okay, their distance to the origin is the same, but sine of theta is positive, but sine of negative theta is negative. So we could say that cos theta is equal to cos negative theta, but sine of theta is equal to negative sine of negative theta. Or in other words, sine of negative theta will be equal to negative sine of theta. Well, how does that help us? Well, let's have a look at what we've got here with our conjugate. Okay, cos of theta we could write as cos of negative theta we could write as cos of theta. Sine of theta we could write as negative sine of theta. So in other words, then our complex conjugate could be written as R times cos theta minus I sine of theta. And that's summarized there. Okay, the complex conjugate Z of Z is R cos theta minus I sine theta, as opposed to R cos theta plus I sine theta. Alright?